Welcome to BMS NetPro Academy and to Book 3, Building Automation Controls Engineering. In this orientation, we are setting the expectations for the course. This course is not just about programming controllers, it is about understanding what the building must physically do, writing sequences that can be tested, and using evidence to prove performance. As we move through the modules, keep one question in your mind. What is the required physical outcome, and what evidence proves the system achieved it? By the end of this course, you should be able to reason from the real building first. You should be able to write and review sequences that define modes, transitions, safeties, failures, and recovery. You should know the difference between a command, a position, a proof point, and a real physical result. You will practice using trends and alarms as evidence, not as guesses. The goal is not to memorize slides. The goal is to become more confident making professional controls decisions in the field. The central idea in Book 3 is simple but powerful. A building automation system is a decision-making machine connected to the physical world. Sensors report conditions. Controllers compare those conditions with requirements. Programs decide what to do next. Actuators move valves, dampers, drives, relays, and stages. But the real question is always physical. Did the building respond correctly? This course teaches that professional habit. We do not judge control work by whether code runs. We judge it by whether the controlled result is stable, safe, reliable, maintainable, and verifiable. This slide shows the engineering chain we will use all the time. Start with the physical process, then identify the sensor that represents that process. The controller receives the input, and the program logic decides what correction is required. The actuator or final control element changes the building. Then we need proof and outcome evidence. If the sensor is wrong, the logic may make the wrong decision. If the actuator does not move, the command is meaningless. If the process does not respond, the control loop is not successful. This is why the course keeps returning to evidence. Book 3 is field-oriented. We will use examples from hospitals, schools, offices, central plants, laboratories, and unitary equipment. In a hospital, the wrong pressure relationship can affect containment. In a school, a poor schedule or ventilation strategy can affect comfort and air quality. In an office, energy optimization can create complaints if the physical limits are not respected. In a plant, staging from a single bad signal can waste energy or cause instability. The habit is consistent. Verify the real equipment response before changing logic. One of the most common mistakes in BAS troubleshooting is confusing command with proof. A graphic may show a fan running because the BAS sent a command, but the drive might be in hand mode. A valve may show position feedback while the stem or linkage is disconnected. Even real actuator movement may not create the required flow, pressure, or temperature response. In this course, we separate command, position, proof, and physical outcome. That separation keeps troubleshooting honest and protects us from blaming the wrong component. This course uses a repeatable diagnostic method. First, define the failing outcome. Is the room warm? Is pressure unstable? Is the chiller short cycling? Then sketch the physical process, verify the measurement, review the active mode and logic, prove the final control element, then test recovery. This prevents random troubleshooting. It also helps a team work from the same evidence. A good technician and a good controls engineer may have different tools, but they should be able to agree on the same evidence path. The Controls Engineer's Oath is the professional standard for this course. We begin with the physical process. We verify measurements before trusting conclusions. We write sequences that define modes, transitions, failures, and recovery. We do not confuse command, position, proof, and result. We design alarms for action and trends for evidence. We test what the system must do, not merely what the screen displays. And we document logic so another qualified person can understand and maintain it later. Here is the learning path. Part 1 builds the control foundation: feedback, process dynamics, PID, measurement confidence, final control elements, states, modes, priorities, and safeties. Part 2 applies that foundation to airside sequences. Part 3 moves to central plant control. Part 4 addresses software architecture, priorities, scheduling, alarms, trends, graphics, documentation, and integration. Part 5 brings everything into commissioning and optimization. The appendices become the tools and templates learners use in the LMS and capstone. Inside LearnWorlds, each module should feel like a complete professional lesson. The learner watches short avatar videos, reads the relevant part of the chapter, uses a practical tool, completes a knowledge check, and then applies the concept in a field-style assignment. The important point is that every module produces something useful. Sequence notes, a diagnostic checklist, a test plan, an alarm review, or a commissioning artifact. The course should build a professional workbook, not just a certificate record. Before we move into Module 1, remember the orientation message. Controls engineering starts with the physical process. We verify measurements before changing logic. We write complete sequences with modes, priorities, failures, alarms, trends, tests, and recovery. We use alarms to guide action and trends to gather evidence. And when we commission, we test the required behavior of the installed system. In Module 1, we begin with the foundation, automatic control and the closed loop. Let us finish the orientation with 3 questions. First, a fan is commanded on. What would prove useful operation? Second, a trend looks unstable. What do you check before tuning? Third, a sequence is missing failure recovery. Why is that a risk? These questions preview the professional thinking used throughout Book 3. The correct answers are not only software answers. They require physical evidence, measurement confidence, defined states, and testable recovery. Complete the knowledge check in the LMS before moving to Module 1,